Welcome to the Standex Meter RF Read Relays presentation, Part 2 Product Training Module. This second RF presentation assumes you have already heard the first Standex Meter RF Part 1 presentation. If you have not, I suggest you go through that one first. Understanding the simple physical layout of a read relay makes it easy to design and test read relays for RF and fast digital pulse applications. RF is dependent on the physical layout or signal path it takes while going through circuits and the components that make up those circuits. We will show you how the physical layout of the read relay will have a direct bearing on the RF signal's success going into and out of the read relay. Coupled with the read relay's physical layout, the materials making up the read relay are also important. The characteristic impedance Z was already introduced in the Standex Meter's RF Part 1 and will be one of the parameters we will focus upon while looking at the materials and geometry of the read relay. For best RF performance, the characteristic impedance must be consistent along the entire signal path. This includes the entry and exit points in and out of the read relay. Most RF circuits today are 50 ohms. So, at any given point at the entry through the read relay and exiting the relay, the characteristic impedance must be maintained at 50 ohms. The designer will need to know how to calculate the characteristic impedance to make sure our design meets the 50 ohms at all points. The characteristic impedance is a vector composed of three components: the pure resistance of the circuit, the capacitive reactance, and the inductive reactance. The impedance is given by the mathematical equation Z equals the square root R2 plus XL minus XC squared, where XL and XC are defined by XL equals 2 pi FL and XC equals 1 divided by 2 pi FC. And XL is the inductive reactance in ohms. XC is the capacitive reactance in ohms. R is the DC resistance in ohms. Z is the impedance in ohms. F is the frequency. L is the inductance. C is the capacitance. In this case, R is the DC resistance of the signal going through the relay. XL is the inductive reactance generated from the inductance in the signal path. And XC is the capacitive reactance generated from the capacitance, which is made up of the physical characteristics of the reed blades and the shield running down the internal length of the relay. All of these parameters are physical and measurable. The final set of equations needed to calculate the characteristic impedance are for the calculation of the capacitance and inductance as given above. Please note, these parameters are all geometric and measurable or are material constants that can be looked up in tables. All of the physical geometries to be presented will use these sets of equations or some variations thereof to calculate the characteristic impedance. The impedance can be calculated at any point along the signal path. In this manner, we will know ahead of time if we are meeting the 50 ohms. Therefore, the RF signals look at the distributed impedance along the signal path. So when the RF comes upon a change in impedance, say 55 ohms instead of 50 ohms, part of the signal where the impedance has changed will be reflected backwards. This translates into an actual loss in signal strength. The entire signal path is critical. Any changes in the signal path will change the impedance at that point, creating a reflection and loss of signal. The shield, being the ground part of the signal path, is very important to maintain impedance consistency. Any changes in the shield geometry will result in signal loss. It is the signal path, the shield, and the material between them that determines the impedance. The above image shows the critical components that exist within each RF read relay. One can see the double shield connectors on each side of the relay. The 4 shield points in the 2 signal leads make up the key components of the RF relay. The 2 coil leads turn the relay on and off, opening and closing the reed switch contacts, but play no role in the RF characteristics. We will now show you how to calculate the characteristic impedance for the different geometries encountered as the signal enters, passes through, and leaves the reed relay. This includes calculating the flattened section and the circular section of the reed blades. We will also calculate the flattened leads as they exit the reed relay and as they are mounted on a substrate or PCB. From the geometry above, one can see for a flat reed switch blade, the impedance equation shows the complete dependence on the geometry of the reed relay. This equation shows how the physical design of a reed relay can clearly control and enhance the RF performance by maintaining a consistent characteristic impedance. Once again, the characteristic impedance for a circular reed switch lead is presented, and the physical characteristics are needed to determine the characteristic impedance. Calculating and designing for 50 ohms into, through, and out of the relay will generally meet most circuitry impedance. With a good RF design for a reed relay, there will be 2 shield leads on each side of the signal lead. This will allow for a better controlled impedance as the leads exit the relay. Above, these leads are shown with their geometric dimensions still within the molded plastic. Since this is a general lead configuration, there are standard programs available to simply add your dimensions to the program, which in turn will output the exact characteristic impedance. Above, these leads are shown with their geometric dimensions after they have exited molded plastic. At this point, the shield and signal leads encounter a ground plane where the leads are mounted on a substrate. Since this is also a standard lead configuration with ground plane, there are standard programs available to simply add your dimensions to the program, which in turn output the exact characteristic impedance. Above, these leads are shown with their geometric dimensions mounted directly to a PCB with a ground plane substrate. Again, a standard program will crank out the exact characteristic impedance. The reed relay manufacturer and the customer must work closely together, defining and laying out this geometric area to maintain the 50 ohms impedance. When the customer does not get the RF characteristics that they expect, this is usually the area or location that should be carefully analyzed. To get the ideal RF performance requires the customers using the reed relays to coordinate the PCB layout to accept the reed relay leads maintaining a 50 ohms impedance. The customer's testing should compare or be similar to Standex Metter's testing approach. If this is not the case, the RF performance will not be comparable. To match Standex Metter's RF reed relay testing results, the customer many times will need to add some circuitry in the form of inductance and capacitance at the input and output of the reed relay. This tweaking is usually required because the geometries of the PCB and the reed relay will be slightly different. The customer is also matching other components on the PCB nearby the reed relay as well. Special test fixtures are required to test reed relays and other electronic components. The proper design of the test fixtures is crucial in determining the true RF performance of the reed relay. Special calibration fixtures must also be designed for proper RF testing. Their designs are just as critical as the test fixture design. All the testing information can be shared directly and electronically with our customers. Our customers can use our electronic information and input into their software to see how our reed relay will function from an RF standpoint in their circuitry before ever having to place the actual reed relay on their circuit board. Controlling the 50 ohm impedance path going into the reed relay, through the reed relay, and the other end of the reed relay is the first important step. If there's any change in the 50 ohm impedance, part of the signal will be reflected back. This represents a signal reduction when leaving the relay. Shortening the signal path will improve the RF characteristics of the reed relay. Standex Metter's LP series was one of its first RF relays. With new relay designs, we have dramatically reduced the overall signal path. The signal path starts at the bottom of the PCB at point A, goes through the PCB up into the junction of the reed switch, through the reed switch, and down to the bottom of the PCB. The distance within the relay from point A to point B is approximately 0.8 inches, with the added length from the bottom of the PCB on both sides and up into the relay. This offers much room for improvement, as we will show you. Above the SIL and MS reed relays are single inline relays. On the SIL relay above, the distance within the relay from A to B is approximately 0.70 inches, which is a little shorter than the LP relay, so it should have better RF characteristics because of the shorter signal path. The MS relay is even better and is only 0.50 inches inside the relay from point A to point B, so the RF characteristics will be better still. Note, however, the reed relays still have their inputs and outputs going through the PCB on both sides of the relay. To further reduce the signal path, the above surface mount relays have eliminated the signal path length of going through the PCB twice as shown with the CRF relay. One can easily see the surface-mounted reed relays have much better RF characteristics when comparing them to whole relays, where the signal must pass through the PCB twice. The signal path from A to B on the CRF is only 0.30 inches. Another way to further reduce signal path and increase RF performance is to package more than one relay in a package. In the top image, two CRF reed relays are shown in line. The signal path goes from A to B. As the signal leaves the first CRF reed relay, it goes down to the PCB and then transverses the short distance to the second CRF relay, where it then goes up the lead and into the second CRF relay. In Standex Metter's RM series shown in the lower image, there are two relays within series packaging, so the leads never exit the package. The signal simply goes from one reed relay directly to the next relay, all on the same plane, further reducing the signal path. As discussed in the first RF discussion, the RF isolation is the ability of the reed relay to isolate the signal when the relay contacts are open. Because of the capacitance that exits across the contacts, some RF signal can leak across open contacts, particularly as you increase RF frequencies. When you increase the reed switch gap distance, this decreases the capacitance, which in turn improves the signal isolation. The gap distance increase is directly related to an increase in the ampere turns of the reed switch. This will require a stronger coil, requiring more power to operate or close the reed contacts within the relay. Half T and full T switching configurations will also improve isolation. In the above, there are two RF reed relays, with one having open contacts and the other closed to ground. In this case, the open contacts keep the majority of the RF signal blocked, and any leakage from the open contacts will be shunted to ground through the closed contacts. In the full T, there are three RF reed relays. In this case, it offers the same characteristics as in the 0T with the addition of the third relay, where it further isolates the signal with its open contacts. Like almost anything, when you make changes to improve one area, other areas may suffer. This is the case with the half T and the full T configuration. By adding additional reed relays, we have added signal path, which will reduce the insertion loss and lower the overall RF frequency response. This may be acceptable depending upon the actual application and its required RF frequency. The listing above shows the frequency ranges for several Standex Metter RF series. You will note they range from DC up to 7 GHz. As you go down the listing, the relays become smaller and smaller, with the CRF being the smallest. The graph above shows the insertion loss up to 7 GHz for the CRF RF reed relay series. When the signal falls off to -3 dB, this represents the signal has lost 50% of its signal strength and is considered the end limit of the frequency response. Shown above is the isolation graph for the CRF relay. Most customers like the isolation better than -20 dB. However, there are other components that can be placed in series with the reed relay, which will add to the overall circuit isolation. Reed relays represent excellent RF switching components, both for continuous wave RF and digital RF pulses. The reed relay RF design is most dependent on its geometric and the material makeup. Careful design and material selection is critical. Customers using the RF reed relays must match the impedance entering and exiting the relay. Maintaining a pure 50 ohm impedance on the PCB through the reed relay and back onto the PCB is critical to maintain the RF path.